السلام عليكم. مع حضراتكم الدكتور أحمد فايد، أستاذ مساعد الكيمياء التحليلية. هكون معاكم على مدار محاضرة أشرح فيها جزء من الكورس في سي 203 وبرضه 603. الكورس ده هنتكلم فيه على بارت هو الكومبلكس فورميشن تايتريشن، وهنشوف النظرية بتاعته والتطبيقات، جزء من التطبيقات. I'm Dr. Ahmed Fayed, Associate Professor of Analytical Chemistry Department. I will be with you in one lecture to explain the complex formation titration as a part from our course 203 and also 603. So let us begin. We have discussed before theories of acid-base titration. One of them was Lewis theory. Complexometric titration is considered to be one of Lewis theories, where the acid part is the electron acceptor and the basic part is the electron donor. We shall review together, just for our memory, the types of bonds. There is an ionic bond, such as the sodium chloride. There is a covalent bond between two atoms to form a molecule, such as the oxygen. And in our case, in complexometric titration, the type of bonds between the two moieties forming a complex is a coordinate bond between what is called the central metal ion and a ligand. Definition: complexometry is a volumetric method, involves reaction of metal with ligand to form a complex, where the central metal ion is the electron acceptor, the ligand is the electron donor. The ligand should contain a donating atom, which donates the electron. They are called a heteroatom, such as the nitrogen, oxygen, and sulfur, to form the coordinate bond between the ligand and metal. So, complex formation is a type of acid-base reaction according to Lewis theory, where metal ion is Lewis acid, the electron acceptor, and the ligand is Lewis base, which is the electron donor. At the end, they form together a weakly ionizable, stable complex. Of course, for a reaction to be completed, the end product should be more stable than those moieties at the beginning of the reaction. Simple diagrammatic form, where the central metal ion, which is usually positively charged, either 2, 3, 4 positively charged, with a ligand which donates the lone pair of electrons to form a coordinate bond, thus forming a complex which is weakly dissociated stable compound. Types of ligands. Ligands could be categorized or classified depending on the charge. For example, neutral ligand as the ammonia, charged ligand as the cyanide. In order to make this a little bit easier how they are bonded together, you can see the copper, which is 2 positively charged, is surrounded or coordinated, bonded by 4 moieties of ammonia. A question: well, what's the valency of the formed complex? Usually the valency of the complex is the algebraic sum of the valency of its components. In our case here, the copper amine complex will take, as a complex, will take 2 positively charged, because the ammonia are neutral and the copper is 2 positively charged. Coordination number. Coordination number is the number of binding sites between the central metal ion and the ligand. It could be 2, 4, 6. As a definition, coordination number is the number of bonds formed by the central metal ion with ligand. Formerly discussed. Example, the copper amine. You can see that the coordination number here is 4. Why 4? Usually we say that it is double the valency of the central metal ion. Copper here is 2 positively charged, so the coordination number of copper is 4. It depends on steric factors and electronic configuration of the metal. Typical values of coordination number are 2, 4, or 6, even numbers. Another example, like the silver and cyanide, you will see that the silver should take 2 ligands or 2 cyanide moieties. The end result of the valency of this complex is -1. Why? We took 2 parts of the cyanide multiplied by -1 and 1 part of the silver, which is 1 positively charged, so the end result will be 1 negatively charged complex of silver cyanide. Same goes here for copper and cyanide, and same here with silver and amine. Aquo-complex. Usually our metal sample is dissolved in water. Since water has the oxygen, and oxygen is one of the heteroatom previously discussed, they will form a complex with the metal called Aquo-complex. This complex, either it is labile or it is non-labile. Labile, that means that the water molecules surrounding the metal forming the Aquo-complex are easily substituted by any other ligand that could enter the reaction. It doesn't need any vigorous or extensive conditions of the reaction. However, non-labile or inert Aquo-complexes, they are very slow to be replaced. Here the ligand has some difficulty to replace the water molecules, and it needs heating, sometimes vigorous shaking, just to be replaced. In that case, we call it a non-labile or inert Aquo-complex. These metals usually form non-labile or inert Aquo-complexes. Aluminium, cobalt, chromium, and ferric should be good memorized, because we will see in the second lecture how we could analyze it. It will not be analyzed directly by simple titration. So Aquo-complexes is the tendency to form complex is inherent property of all metal. Therefore, metals form with water Aquo-complex, which is solvated metal ion, as oxygen of water donate electrons to metal ions. Complexation reaction is a replacement of solvent molecules by a ligand. This replacement by a ligand can be repeated several times, but not forever, till the central metal ion takes an optimum number of ligand governed by the maximum coordination number of the metal ion. Just to remind you, usually the coordination number is double the valency of the central metal ion. So the Aquo-complexes could be divided into labile or inert non-labile. Some Aquo-complexes undergo substitution reaction very rapidly, and the complex is said to be labile, for example copper and nickel. Others undergo substitution reaction very slow, and the complex is said to be non-labile, such as aluminium, chromium, ferric, and cobalt. Another classification of the ligand is the points of attachment between the ligand and the central metal ion. So, if the ligand is attached to one point with the central metal ion, it is called unidentate. If it is attached with more than one point, then it's called polydentate. Then the polydentate is subclassified into bidentate, tridentate, tetradentate, depending on the number of points of attachments with the central metal ion. Unidentate ligand, diagrammatic form just to make it a little bit easy. For central metal ion, one point of attachment forming the metal ligand complex. On the other hand, polydentate ligand form a chelate. A chelate is a ring structure, weakly dissociated complex, where the ligand is a polydentate attaching the metal with more than one point, and in such case the ligand is called a chelating agent. Examples from the polydentate ligand. Let us begin with the bidentate ligand, such as ethylene diamine with copper. It forms a ring structure, a chelate. 8-hydroxyquinoline, ring structure with magnesium. Orthophenanthroline with ferrous, also a ring structure chelate with the ferrous. 6-membered ring, such as acetyl acetonato. Tridentate ligand, for example, diethylene triamine. Tetradentate ligand, like triethylene tetramine or triene. I do not need that you memorize these structures, only you should know the classification and an example from a compound that is related to each subclassification. Another topic is the stability of the complex. Which do you feel or you see it will be more stable? A central metal ion attached to 2 ligands, or 4 ligands, or 6 ligands? Well, eventually, as the points of attachments increase, the stability of the complex also increases. So, by default, you will see that the polydentate ligand, either bi, tri, or tetradentate, are more stable if they form a complex with a central metal ion rather than the unit ligand. Chelates are more stable than complexes formed by unidentate ligand. Again, a chelate is a complex that is formed of a central metal ion and a polydentate ligand. Why? Due to presence of more than one point of attachment of the ligand and the central metal ion. Therefore, a polydentate ligand is preferable as a titrant if compared with unidentate ligand because they react with the metal completely in one step and rapid, forming stable complex leading to sharp end point. On the other hand, any stepwise formation of the complex with a unidentate ligand gives no sharp end point. And what we should know that for quantitative determination, to know the concentration of our sample, we should apply a polydentate ligand to give a sharp endpoint so that we can take the reading more accurately. Simple comparison between the types of complexing agents or the ligand. You will see that the unidentate ligand attached to central metal ion form one point of attachment, forming a soluble complex using ammonia, water, cyanide, or halides as ligand, which are inorganic molecules. And an example of that is the formation of copper-amine complex. On the other hand, polydentate ligands, they are attached to the central metal ion from more than one point of attachment, forming a ring structure complex with metal, which is called a chelate. Ligands at this stage are called chelating agents, and complexes are called chelates. Chelating agents are inorganic molecules which are usually water insoluble, could be determined with gravimetry, but that will be later studied. Except a very important polydentate ligand is water soluble universal titrating agent called EDTA. In titrometry, we always use EDTA for determination of the metal. In such case, the water soluble polydentate ligand is called sequestering agent. This is a simplified table which gives you a quick comparison at different points between the unidentate and the polydentate, taking up from the point of attachments, the reaction, how it will be, the inflection of the titration curve, endpoint, stability of the formed complex, titrometric reaction, and of course some examples. Well, how do you think about these questions? Compare between unidentate and polydentate ligand. You will discuss the previously illustrated points in the table. Ammonia couldn't be used as a titrant. Well, ammonia is a unidentate ligand, and unidentate ligand results in a slow reaction, stepwise, giving no sharp endpoint. Another question, polydentate ligands are used as titrant. We give the advantages of the polydentate ligand, more than one point of attachment, sudden inflection of the curve, one step reaction gives sharp endpoint. Polydentate ligand form more stable complexes than unidentate ligand. All of these questions could be answered with what we have just discussed between the comparison of the polydentate and the unidentate ligands. Well, what are the factors affecting stability of the complex? Stability of the complex is, since the complex is formed between the metal and the ligand, then there are some factors affecting the metal and some factors affecting the ligand. The acidity of the metal, the basicity of the ligand. For the metal, the ionic size and the ionic charge differ compared to the stability of the complex. For the ligand, the size of the ligand, structure of the final chelate, and extent of chelation also differ in the stability of the complex. Factors affecting the stability of the complex. When we should discuss the central metal ion, we say that the higher the acidity or electronegativity of the central metal ion, the higher the stability of the complex, which means that if we increase the density of the positive charge on the central metal ion, it will increase the stability of the complex, because in that case, the central metal ion will grab or take the electrons more rapidly and more aggressively. It is governed by a simple formula or equation where we say the intensity, which is F, is directly proportional to the charge present on the central metal ion, inversely proportional to the radius of the central metal ion. That means if a central metal ion are dense in charges, it will form eventually a more stable complex. If the central metal ion is low in the size or with smaller size, it will also form eventually a stable complex. So the central metal ion of small radius and high positive charge has high ability to form stable complex. Also, just for your information, the principal quantum number, it's a unique number that is present for each central metal ion. They differ also in stability, just to know this phrase as it is. Question: the acidity, what do you think about the acidity of these two central metal ions having the same charge, but they differ in the size? Of course, the smaller the radius, the high density of the positive charge, eventually forming a more stable complex. On the other hand, two with the same radius, the central metal ion, but one of them is more positively charged, this one will form the more stable complex. For example, the ferric cyanide complex is more stable than the ferrous cyanide complex. Again, the formula which discuss the same theory. The second factor affecting the ligand, well, it's the basicity of the ligand. Basicity of the ligand is its electron donating ability. Therefore, ligand must contain electron donating atoms, which are called heteroatom: nitrogen, oxygen, sulfur, and halides. Organic ligands must contain coordinate or acidic group, or both of them. They are classified as such in the table. The ligand, if it is large but not very large, it will easily lose the electrons than a smaller ligand, and thus the electron donating ability will increase and the basicity of the ligand will also increase, giving a more stable complex. Size of the ligand. Two large bulky ligands form less stable complexes than smaller ones due to steric effect. For example, ethylene diamine form more stable complex than other bulky ligands. Structure of the final chelate. The stablest chelates are formed by ligands that form saturated 5-membered ring, or by ligands forming unsaturated 6-membered ring. For example, the copper ethylene diamine complex or the acetyl acetonate. Surrounding conditions. Some stable complexes may not be stable under other conditions. For example, cobalt amine complex is unstable in acidic solution but stable in water. EDTA. EDTA as a titrant in complexometric titration is a universal titrant which is usually used in all titrometric complexometric reaction. EDTA is abbreviated. This is the abbreviation of ethylene diamine tetra-acetic acid. The disodium salt of EDTA is soluble in water, what we have called a chelating agent that is soluble in water, sequestering agent. It forms soluble chelates and is the most suitable titrant. Do not need you to memorize the structure of EDTA. However, to simplify things, this bulky part of the structure we abbreviated by Y. So the disodium salt of EDTA is abbreviated by sodium, hydrogen, and Y. A commercial name of the EDTA is called Complexone 3. Please memorize that, Complexone 3. The following equilibrium is established when sodium, hydrogen, and Y, which is the EDTA, is dissolved in water. Why using EDTA? It has low price. It forms a special hexadentate structure with the central metal ion. It is bonded by 6 points of attachments, either horizontally or vertically, to form a spider web on the central metal ion. It is a typical sequestering agent. It was found that EDTA reacts with different central metal ions in the ratio of 1:1, irrespective to the valency of the central metal ion. You can see here, all central metal ions with different valencies are treated equally with the EDTA, liberating 2 parts of the hydrogen. Therefore, and this is important characteristics should be memorized for EDTA. EDTA is not selective reagent. Central metal ion displace 2 parts of the hydrogen, producing 2 mole of hydrogen. The reaction between EDTA and the central metal ion is according to the molecular weight. Reacts in ratio of 1:1 with all metals, therefore EDTA is used as molar standard. Formation or dissociation of the formed complex is affected by pH. So, the reversibility of the reaction can be prevented by addition of buffer or alkali to shift the reaction forward, hence stability of chelate is increased, always consuming the hydrogen and always shifting the reaction forward towards the formation of a complex. Questions. Why EDTA is used as EDTA standard is prepared as molar solution. They react with the central metal ion in ratio of 1:1, irrespective to the valency. Alkaline buffer is used in complexometric titration. Well, the alkali is put, or the buffer has been added to consume the hydrogen liberated from the reaction, thus shifting the reaction forward towards the formation of stable complex. EDTA is not selective. All of these are questions that could be answered by giving the characteristics of the EDTA. They are universal, they are soluble, polydentate ligands, they react with the central metal ion in 1:1 ratio, irrespective to the valency. Stability and stability constant of complex. Stability of a complex is evaluated by its stability constant or formation constant. Assume a reaction between central metal ion and EDTA. According to the law of mass action, the K equilibrium is the value of dividing the parts after the reaction over the parts going into the reaction. So the K equilibrium represents the rate of formation of the complex. It is called as formation constant or stability constant. The greater the K stability, the greater the rate of forward reaction and stability of the formed complex. In alkaline buffered medium, the K stability is represented as follows. We consume the hydrogen, and the reaction is now between the division of the molar concentration of the complex, or the formed complex, divided by the molar concentration of each of the central metal ion and the EDTA. It was found that reaction producing complex with K stability equals or more than 10 to the power 8 is sufficiently complete at the equivalence point, which is the end point, for a feasible titration. K instability is the opposite of K stability, 1 over K stability, just for your information. Here in this table, we can see a formation constants of various metal chelates with EDTA. Just take a look at it. It's not for memorizing. However, you can see very clearly that the values of the K stability or the formation constant are high when the valency of the metal, the central metal ion, is high. Complexometric titration curve. It is a titration curve between minus log the molar concentration of the central metal ion plotted against the volume of EDTA solution added, where an inflection occurs at the equivalence point, which is the end point. It is clear that the greater the stability constant, the sharper is the inflection and the end point, according to the law of mass action. The effect of pH on the complexometric titration. Again, a titration curve here is illustrated. The effect of pH on the stability of complex, which represent titration of calcium salt at different pH values. It is clear from the titration curve that the stability of the metal EDTA is increased by increasing the pH. Well, if you're a little bit tired, take a 5 minutes break and return back to complete the lecture. Now we shall discuss the detection of endpoint. The endpoint is the phase where the reaction has been completed. So we should know exactly when, because we are performing a quantitative analysis with the aid of indicators. These indicators are classified according to the following: either to be a metallochromic indicators, such as murexide, EBT, xylenol orange, or there are present specific indicators, thiocyanate, salicylic acid, or we can detect the endpoint with the aid of acid-base reactions or electrochemical reactions. It's a matter of muscle gain. The theory is like that. The central metal ion is attached to the indicator, which here is a ligand, to form a complex. This metal indicator complex has a specific color, In order to see the concentration of the central metal ion, we titrate against EDTA. The EDTA will consume the indicator until it replaces the indicator and the indicator is gone out of the complex, and the EDTA complex with the metal is now formed and the indicator is free in the solution. Here, the indicator should have another differentiated different color than the color that he had formed with the central metal ion as complex. This change in color is resembling the end point. So, for the detection of the end point, the metal indicators are complexometric titration. The end point is detected by using metal indicator. Metal indicators are usually complexing agents, ligands. The function of metal indicator can be summarized by the following equation. Metal, central metal ion, with the indicator forming a metal indicator complex, which has a specific color. Then the EDTA replaces the indicator and forming a metal EDTA complex and leaving the indicator free, which should have another color. Therefore, for successful use of metal indicators, the following requirements must be fulfilled. Number 1. Reaction between indicator and the central metal ion must be specific, or at least selective. Central metal ion EDTA complex must be more stable than metal indicator complex. Metal indicator complex must be of sufficient stability. That means it shouldn't be dissociated to give free indicator before complete reaction between the metal indicator and the EDTA. Number 4. The color of the metallized indicator and free indicator must be sufficiently different and intense enough, sharp and point. So I highlighted the most important wording in each point: specific, stable, sufficient stability, and sharp endpoint, the 4S rule. Types of metal indicators. Metallochromic indicators. These are called chromodies or mordants. This type of indicators exhibit a color in free form which is different form from that of metal indicator complex. The chemical structure of these indicators contains acidic and or coordinate basic group, which usually hold heteroatoms. These groups are joined in the electronic configuration system of the indicator. Therefore, any change of this electronic configuration could take place within the pH change. Well, if you can remember, the reaction between the metal and the central metal ion and the EDTA releases hydrogen, and hydrogen could change the pH of the medium. Therefore, it is very important to use a buffer or alkali in the complexometric titration. Why? So it can consume the liberated hydrogen from the reaction of the central metal ion and EDTA. Thus, the reaction and the change of color of the metallochromic indicator is only due to the end point, not due to the pH change. General principle. For determination of central metal ion, we add the indicator, forming a metal indicator complex, which in this case, for example, is purple in color. Then we titrate it with a complexing agent like the EDTA, which is also called a sequestering agent, if you can remember. It consumes the metal indicator and giving a free indicator which should have a different color than the metal indicator complex. In that case, for example, it's now blue. So the requirements of the metal indicator, the 4S rule, again, it should be specific for the metal. It should be sufficiently stable, not to be detached unless the reaction is complete with the EDTA. The stability of the EDTA metal complex should be more than the stability of the metal indicator complex, and a different color should be present in case of the metallized form of the indicator and the free form. Examples of the metallochromic indicators. Murexide. Murexide is the ammonium salt of purpuric acid. It forms a ring structure chelate with a central metal ion, and it's usually used for determination of calcium, copper, cobalt, and nickel. Please memorize these metals for murexide. At pH 9 to 11, murexide contains 4 hydrogens, and the following equation represents the effect of pH on the indicator. We usually select the one in the middle, giving a violet color at pH 9 to 11, above which blue color is experienced, below which reddish-violet color appears. So the following equations represent titration of central metal ion against EDTA in presence of murexide indicator. Again, the central metal ion is reacted with the indicator, forming a metal indicator complex. Then EDTA is being added until the reaction is finished. Metal and EDTA complex is now formed, and the free indicator is liberated with different color. To see and memorize, please, the difference in colors. Murexide, copper, cobalt, and nickel complexes are yellow. Murexide free is purple. Murexide calcium complex is pink. Murexide free is purple. We usually use fresh saturated aqua solution or use fine powder of the murexide. Here we can see the difference in the colors between the metallized form of murexide and the free form of murexide in case of calcium. Second metallochromic indicator we have is eriochrome black tea, or EBT as abbreviated, or it's also called solochrome black. It is used for determination of magnesium, zinc, cadmium, lead at pH 10. Please memorize the central metal ions for EBT and the pH range or the pH that it works in. It also contains 2 replaceable hydrogens. The equation here we select in the middle form of the indicator at pH 7 to 11, above which orange form, below which red wine. The following equations represent the titration of central metal ion with EDTA in presence of EBT at pH 7 to 11 using ammonia buffer at pH 10. Well, EBT cannot be used for determination of copper, cobalt, nickel, ferric, and aluminium. Why is that? Because these central metal ions form irreversible complex with this indicator. That means even if we put EDTA, EDTA will not substitute the indicator from the central metal ion indicator complex. That means they block the indicator. Therefore, the central metal ion should be masked using cyanide before titration involving the use of EBT. This will be thoroughly discussed next lecture. EBT also should be used as fresh aqueous solution or fine powder. Here is the difference in color between the metallized form and the free form of the indicator. Third metallochromic indicator we have is xylenol orange. Xylenol orange is used for determination of bismuth and lead, where the difference in color, also please memorize that, the difference in color between the metallized form and the free form is usually from red to yellow. This table resembling the metals that could be analyzed using xylenol orange, the conditions that it is put in, which usually is the pH range, using for example pH 1 to 3 nitric acid, or pH 5 to 6 using hexamine solution, or 5 to 4 using acetate buffer. The change of color is usually from red to yellow, and some exceptions from purple to yellow, such as the ferric and the mercury. Questions? Why we should carry out complexometric titration in buffered medium? We should state two answers. The first answer is to consume the hydrogen liberated from the reaction between the central metal ion and the EDTA. Why? So that it could shift the reaction forward towards the formation of stable complex. The other answer is forward reaction with optimum stability, yes, sharp change on and color change due to complexation reaction, since the metallochromic indicators are affected by pH. EBT cannot be used for determination of copper, cobalt, nickel, ferric, and aluminium. Why is that? Because they block the indicator. They form an irreversible stable complex with the indicator, and no endpoint will result. So the left part is now discussed. Now the right part is discussed in brief as specific indicators such as thiocyanate and salicylic acid. They are specific for ferric, acid-base, and electrochemical reaction. Specific indicators, thiocyanate. Of course, you have heard about the blood red color that is formed between the ferric and the thiocyanate. Here, the endpoint will not be change of color, but it will be a decolorization of this blood red complex color. The same goes with the salicylic acid, also with ferric, but it gives a violet color, and the endpoint is detected by decolorization of this violet color. There are two other methods to detect the endpoint, which is the acid-base titration, acid-base in complexometry? Yes. If you remember, the reaction between the central metal ion and the EDTA produces 2 gram-mole of hydrogen. This hydrogen liberated is equivalent to the molar concentration of the metal. So, we can titrate the hydrogen liberated against standard alkali in presence of an acid-base indicator such as methyl red. And this will be equivalent to the concentration of the metal. Another way to detect the endpoint that we can use electrochemical reaction, potentiometric and conductometric techniques, which you will study it thoroughly in the instrumental part, I think next year or something like that. Take a 5-minute break and then we shall return back to complete our lecture. The final topic we have today is complexometric titration classification. They are classified according to the way we perform the reaction or perform the experiment to direct, back, and replacement. We shall discuss only today the direct and back. Complex formation titration or complexometric with an O, that means titration with the aid or with using EDTA. There are several requirements for direct titration against EDTA. These requirements are, first of all, stability. Metal EDTA complex must be more stable than metal indicator complex in buffered medium. Suitable pH. If the central metal ion is precipitated at the pH suitable for titration, we should add something called auxiliary reagent, مادة مساعدة. This auxiliary reagent must be added to prevent the precipitation of central metal ion and render the central metal ion available for reaction with both indicator and EDTA. An example, the lead salt is precipitated as lead hydroxide at the pH suitable for titration. What should we do? We should add something like the tartaric acid, which is an auxiliary reagent soluble to form a soluble lead tartarates complex, which is less stable than the lead indicator complex, eventually also less stable than the lead EDTA complex. Diagrammatic illustration of that, we have the lead, we put it in a solution with the tartaric acid to form lead tartarate soluble complex. Then we put the indicator, the lead is now ready for reaction in alkaline buffered medium. While titration against EDTA, the EDTA is replaced the indicator from the lead indicator complex, giving free indicator which has a different color in the free form than in the metallized form at the endpoint. Sometimes buffer acts as auxiliary reagent. During titration of copper salt in alkaline medium, alkali hydroxide precipitate as copper hydroxide, and the reaction with EDTA becomes a slow reaction. Okay, what should we do? Upon using ammonia instead of alkaline hydroxides, the soluble copper amine complex is formed, which is less stable than copper EDTA, and hence the reaction proceeds forward rapidly. Another illustration, copper. Copper in an ammoniacal media forms a copper amine complex, soluble complex. Then we add the indicator, also complex copper indicator. It takes out the copper from the copper amine complex. Then titration against EDTA, EDTA consumes the indicator, forming a copper EDTA complex, and the indicator is set now free with a different color at the endpoint. Number 3, speed. The reaction between central metal ion and EDTA must be rapid. If the reaction is slow, then it should be catalyzed. Several impurities. The presence of traces of other metals as impurities may compete with the ion to be estimated and block the indicator. Give you an example we had discussed earlier. In case of titration of calcium and magnesium with EDTA, when we use EBT, some traces of other metals such as copper, cobalt, nickel, and ferric are frequently present and produce similar difficulties in this titration. Hence, what should we do? We should mask this indicator by reducing such metals using something like ascorbic acid, then complexing with cyanide. We will see that as the masking and demasking agent at the end of the lecture, forming a more stable complexes than their EDTA. So, for a direct titration, there are the 4S rule for a requirement that a titration to be directly done. Stability, suitable pH, auxiliary agent, speed of reaction using a catalyst. Several impurities could be then masked. The second category of the complexometric titration, we use a back titration. This titration is used when we have a metal A and we cannot analyze it with the aid of direct titration. In this case, we add a known excess EDTA. Part of this EDTA will be consumed as the volume and quantity of metal A. Forming residual EDTA will be back titrated with metal B, so the titrating agent in our case now is not EDTA but metal B. And the endpoint will be reversed. Why? Because we put the indicator in its free form from the beginning of the reaction, and at the endpoint the indicator will form a complex with the metal B, and the endpoint now, the color is reversed from the free form to the metallized form. And let me illustrate better. Central metal ion sample. We add known excess standard EDTA. Part of this EDTA will be consumed resembling the volume and quantity of the metal. Then the residual EDTA will be titrated against standard magnesium or zinc metals using EBT as indicator, and the endpoint now will be reversed from the full blue to the wine red color. If you want to calculate the concentration of the metal, we use this equation, known excess EDTA minus the residual EDTA, and then multiplied by the factors 1000 divided by the millis of the sample. So when there's a question, when we can use the back titration, it is carried out in the following cases. The first one, when the central metal ion is precipitated at the pH suitable for titration. For example, if we want to determine calcium salt in presence of oxalate, calcium salt reacts with EDTA at pH 10, where calcium is precipitated as calcium oxalate. So, the calcium in the calcium oxalate reacts slowly with EDTA, therefore we can carry out the back titration. Number 2, if a suitable indicator is not available. Number 3, for determination of insoluble substances such as barium sulfate, lead sulfate, and magnesium phosphate. The fourth one we have discussed earlier in this lecture. If the reaction between the central metal ion and EDTA is a slow reaction, for example, reaction of central metal ion which forms inert stable aquo-complexes. If you remember, we have two kinds of aquo-complexes. The labile reaction is fast, and the inert or stable aquo-complexes. And here we replacement of the water by EDTA. The process needs heating and needs vigorous shaking, as with the metals aluminium, cobalt, chromium, and ferric. So this reaction will need a back titration method. Diagrammatic illustration. Calcium oxalate in acid media, alkaline buffered media, which is very crucial for complexometric titration, makes a calcium oxalate precipitate and can't be reacted with EDTA. Calcium oxalate in acid medium, non-excess EDTA, alkaline medium using a buffer, and the reaction of the residual EDTA using zinc sulfate, and the endpoint will be the change of color if we use EBT from full blue to wine red, from the free form to the metallized form. Manganese in ammoniacal media forms a precipitate of manganese hydroxide, can't be directly used for determination of manganese using EDTA as titrant. So we use the technique of the back titration in this case. Insoluble powder. The powders of barium, lead, sulfates, and magnesium phosphate can't be used directly. Then we should follow the indirect way or the indirect titration technique. If we want to analyze calcium using EBT, calcium usually or directly analyzed by using murexide, if you remember. But if we want to use EBT, we follow the back titration technique. The calcium sample, we put known excess EDTA. Then the residual EDTA will be back titrated using magnesium sulfate, using EBT as indicator, change of color from blue to violet. The aquo-complexes, I think you have seen such slide before. The water molecules surrounding the metal samples, and one of them is a non-labile or inert aquo-complex. Very slow reaction if we want to be replaced by the EDTA using heat and vigorous shaking, then the EDTA could replace the water molecules. This slow reaction cannot be done or performed if we want accurate results. Therefore, with the aid of back titration, we can analyze such metals as aluminium, cobalt, chromium, and ferric. Examples. To analyze aluminium sample is treated with known excess standard EDTA. Amount of EDTA is consumed at pH 7 to 8, which resembles the quantity or the concentration of aluminium. And then the residual EDTA at a buffer pH 10 is treated with standard zinc sulfate, and zinc EDTA is now produced. At the end point, the EBT is turned from blue to wine red, the indicator from the free form to the metallized form. And this reaction resembles what is happening: aluminium and EDTA giving aluminium editate, zinc and EDTA giving zinc editate, and the first drop of zinc will react with the indicator, giving the zinc indicator complex, wine red. The same goes with chromium salt, as mentioned under aluminium, with the pH 6 using acetate buffer and titrate residual EDTA at the same pH against lead nitrate using xylenol orange as indicator. Here also the endpoint is flipped, not from red to lemon yellow, but the other way around, from the free form to the metallized form of the indicator, the xylenol orange. So for back titration, there is no suitable pH that could be that we can analyze the sample in. There is no suitable indicator, a slow reaction, and an insoluble substances. These all will cause the effect or will cause the use of the back titration technique. Well, finally, can we use complexometry in more complicated research? Yes, they found that the multidentate ligand can bind with a radioreactive metal to form a monoclonal antibody, or MAB. This MAB is a protein that could bind with a specific feature on the tumor cells, delivering toxic dose of radiation. Thus, drug targeting idea came. Also, in the World War I, they were bombing soldiers with toxic gases, such as arsenic gases. The British have discovered that they can use a chelating agent that could be chelated or adhered with the arsenic, called British anti-leucocide or BAL, dimer-caprol. Then it will form a soluble compound entering the bloodstream, allowing its removal from the body with the aid of the excretion, the normal excretion methods via the kidneys and liver. Well, we have finished today's lecture. I hope that you have learned a little bit from it. I hope that I was clear enough. For any kind of questions, please do not hesitate to ask. Thank you.